So now I'm going to start looking at the test that we just gave, fall 2021. Problem 1. Draw a valid Lewis structure for PO4, 3 minus. Phosphorus has 5 valence electrons. Oxygen has 6. 6 times 4 is 24, plus another 3. 5 plus 3 is 8. 8 plus 24 is 32. P in the center. Oh. That uses 8. I'm down to 24 electrons. Put 6 around everything. That in itself is a valid Lewis structure. I've used up all 24 electrons. Is this the best Lewis structure? No, but this is definitely a valid one. A alternative would be to make a double bond between one of the oxygens and the phosphorus, thus generating 0, well, one less formal charge, but giving phosphorus an expanded octet. So now we'd have 3 formal charges instead of 5. But either way, either of these structures would work. This is an example of a resonance structure that they can resonate between the two, and this double bond can resonate to all 3 other positions. Problem 2, we need our reactivity chart on the right to help us. So the question is, which of the following reactions would occur? Would aluminum replace iron? Would magnesium replace sodium? Would barium replace silver? To answer this question, you need to find which metal is higher on the table. The pure metal replaces the compound metal if it is higher. So here is barium, here is sodium, here's magnesium, here's aluminum, here's iron, and way down on the bottom, just out of frame, is silver. So will barium replace silver? Most definitely. Will aluminum replace iron? Certainly. But will magnesium replace sodium? No. No. So the correct answer is answer C. Now, while this problem 3 was not meant to be difficult, if you did not remember what a resonance structure is and how to draw one, it could be most difficult. So start with all the same number of single bonds. So you would keep all the same initial bonds. I'm just drawing the carbons first before everything else. Now the key here with a resonance structure is a lone pair on a different atom is going to swing into a nearby bond and kick out a nearby double bond. So what we're going to have is this, and so you would have this as your resonance structure. So the lone pair carbon would swing into this double bond, thus kicking out this double bond. And so this is your enolate structure. For those who will eventually take organic chemistry, that would be the carbonyl group, and this was gone to an enol, basically saying a double bond with an O, especially an OH. Okay. Problem 4. What is the oxidation number of the atoms in this reaction, and is this an oxidation reduction reaction? I'll start with the easy ones. Any atom by itself left charged is going to be that charge itself. So H plus is going to stay +1. Next thing to note, H plus in a compound is almost always +1. Now O within a compound, except for a few rare cases, is going to be minus 2. Minus 2. In this case, this is also minus 2. It's minus 2 and plus 1. So oxygen does not change. Now let's look at chromium. If this is minus 2, negative 2 times 4 plus chromium must equal negative 2. So negative 8 plus chromium would equal negative 2. So chromium has to be plus 6. Now here, there's 2 chromiums minus 2 times 7 also equals negative 2. So negative 14 plus 2 chromiums equals negative 2. The only way this equals negative 2 if 2 chromiums together are positive 12. So splitting up the positive 12 by 2, you get plus 6. Is chromium being oxidized or reduced? The answer is no. Chromium is staying plus 6 and plus 6. That's a trick question. It looks like it's being oxidized, but in actuality, it's not. You're basically having CrO3 plus a O2 minus goes to 2 CrO3 plus a O2 minus. 2 chromium goes to chromium, 2 CrO6 plus another O would be O7. What is the molecular geometry of bromine what this should be bromite. So with O1 minus. Bromite. So bromine is 7. Oxygen is 6 times 2 is 12 plus 1 because it's negative 1. Means 8 plus 12 is 20 electrons. Start with bromine in the center. O and an O. That's 4 electrons. We're down to 16. Put our 6 on each oxygen. Give it an octet. We're down to, we used 12, so we're down to 4. Slap 4 on the bromine. Now we have, what is our electron geometry? We have how many electron domains? 1, 2, 3, 4. So it'd be a tetrahedral electron geometry. But what is its actual shape? It is bent because there's 1, 2 lone pairs. 2 lone pairs. Looking at the valid Lewis structure for this organic compound. Fragmented at this. Please note that this 2 goes to the whole in parentheses. Every carbon should have 4 bonds. Every halogen should have 1 bond, 3 lone pairs. So I'm going to actually start from the right again. It's actually going to be easier. So halogen, 3 lone pairs, 1 bond. Carbon should have 4 bonds. 2 bonds are unaccounted for. So I'm going to, since we have CH2, CH3, CH2, CH3, but 2 of them, structure like going off the page right there, and a C, H, H, C, H, H, H. So here's our 2 ethyl groups. 2 ethyl groups coming off of a CHCl. If you're in organic chemistry, you would call this 1, 2, 3, 4, 5, 3-chloropentane. But that is neither here nor there. Okay, moving right along. Determine the formal charges of all atoms involved in the following structure. Please note the overall formal charge is -1, but you don't need this to solve this question. To do formal charges, we need valence electrons minus actual electrons. Valence for sulfur is 6, carbon is 4, N is 5. How many does sulfur see? 1, 2, 3, 4, 5, 6. formal charge of sulfur is 0. Carbon sees 1, 2, 3, 4. Minus 4 is also 0. Nitrogen sees 1, 2, 3, 4, 5, 6. So the formal charge on nitrogen is -1. That is our formal charge. Notice all formal charges should add up to the overall charge. -1 plus 0 gives you -1. Well, that works. What is the electron geometry of antimony tetrafluoride anion? Antimony is group 5. To check there. Fluorine is group 7. 7 times 4 is, let's see, 28. And 1 minus. 28 plus 6 gives you 34. Antimony. Put a 4 F's around it. That uses 8. We're down to 26. Put lone pairs around this. That's 6 electrons each. That's using up 24 of our 26 electrons. So that means the last pair must go on this antimony. With that in mind, how many electron domains does antimony see? 1, 2, 3, 4, 5. 5 electron domains means it's trigonal bipyramidal. Does it matter that one of them is a lone pair? Not in the electron geometry. The electron geometry only regards straight electron domains and not our lone pairs. We don't care which one's a bond and which one's a lone pair. Yes, this would be seesaw in the case of molecular geometry, but not an electron. How many sigma and pi bonds are in the following molecule? Count every bond once, and that will be your sigma. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sigma. Now, every bond that's left would count as your pi. So 1, 2, 3, 4. 13 sigma, 4 pi. That would be that structure. Determine the hybridization of the following atoms in this heme molecule. Please note, these weird bonds are from nitrogen donating electrons into here. But all lone pairs are accounted for. So carbon 10 right here. How many electron domains? 1, 2, 3. What must this be? sp2. Nitrogen 24. How many electron domains? 1, 2, 3. sp2. The iron. How many things are coming off the iron? 1, 2, 3, 4, 5, 6. It's going to be octahedral sp3d2. Carbon 29, way over here. 1, 2, 3. sp2 and 31 over here. 1, 2, 3, 4. The only sp3 hybridized atom in this molecule. Right there. I mean, technically, I guess the oxygens are sp3 hybridized, but I mean, and that guy's sp3 hybridized, but everything else. Looking at our first net ionic equation, we must look at comparison. Break this down into the total ionic before making the net ionic. Aqueous, 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 solid. Now, where would you get that? You would get this from this chart. Magnesium, lead, magnesium sulfate, lead sulfate, nitrate, lead nitrate. Lead sulfate is solid, magnesium nitrate is aqueous. That means every aqueous would break apart. Every solid would stay together. So it would have Mg2 plus, SO4 2 minus, Pb2 plus, 2NO3 1 minus, yields Mg2 plus, 2NO3 1 minus, and PbSO4 solid. So when all said and done, we cancel out our magnesiums, we cancel out our nitrates. The net ionic is Pb2 plus, aqueous, and SO4 2 minus, aqueous. Go to PbSO4 solid for the correct answer for that one. Draw a valid Lewis structure for HCN. H is 1, C is 4, N is 5. Add those up, 6, you have 10 electrons. C is in the center. That uses 2. We are down to, uses 4, down to 6. Place them there. We're out of electrons. But now we must give carbon an octet. So double bond. Now it's one closer. Double bond or triple bond. So we have H, C triple bond N with one lone pair. That's the valid Lewis structure for HCN. AlCl4. AlCl4. Aluminum is 3. Chlorine is 7. 7 times 4 is 28 plus 1. 28 plus 4 is 32. Al, Cl, 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 Cl. That uses 8, so we're down to 24. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That uses up all 24 electrons. That is a valid Lewis structure. That's all you have to do. That one's not that bad. Okay. What is the electron geometry? What is the molecular geometry? What is the molecular geometry of NO3 minus? N is 5. O is 6. 6 times 3 is 18. Plus 1. 6 plus 18 is 24. N, O, O, O. That uses 6. We're down to 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Out of electrons. Make a double bond to stabilize this. What is the molecular geometry? 1, 2, 3 things coming off the nitrogen. It must be trigonal planar. Trigonal planar. Draw a polar version of PCl3F2. Basically, this guy should be trigonal bipyramidal, but you can check. Middle. We should have 7 times 5, so 35 plus another 5, 40 electrons. That's enough for 5 bonds, which would be 10, and then 6 times 5 would be the remaining 30 electrons. So trigonal bipyramidal has this shape. Now, the only way to really screw this up is by putting all 3 CLs in this plane. As long as there's one CL here, you are good. You do CL, 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 F, F. That is polar. Or you could do it like this. Cl, 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 F, F. And that would also be polar. On problem 16, this one kind of gave some people some problems. So we have to look at here. We have ammonium chloride and sodium hydroxide goes to ammonia, NaCl, and water. I told people to treat ammonia like liquid. Technically, it's aqueous, but we'll put it's a liquid for now. The whole idea is that it's a weak electrolyte. It does not break apart. Water is a liquid, so we just have to check our other stuff. So ammonium, here's our chloride, here's our sodium, and our hydroxide. Sodium hydroxide, sodium chloride. Ammonium chloride, technically ammonium hydroxide, but that's not really either way. So the idea here, this breaks apart, this is going to break apart, this is going to break apart. So you would have ammonium plus 1, chloride minus 1, sodium plus hydroxide minus goes to NH3, let's just call it a liquid, Na plus, Cl minus, H2O, it's a liquid. So Cl, Cl, Na, Na. A reaction becomes NH4 plus aqueous and OH minus aqueous goes to NH3 liquid and H2O liquid. But technically this is aqueous, but we'll let it slide for the simplicity here. Last page. So classify these following reactions: combination, decomposition, single displacement, double displacement. So combination, 2 become 1. Decomposition, 1 becomes 2. Single displacement, A plus BC goes to B plus AC. Double displacement, we have the double. So starting off, we have acetic acid and barium hydroxide go to water, which is HOH, and barium acetate. That's a classic case of double displacement. That's also acid base. Potassium chlorate goes to potassium chloride and oxygen. Classic case of decomposition. One thing becomes 2. H2O and CO2 forms carbonic acid. That's a classic case of 2 becomes 1. Combination. NaCl and F2 becomes NaF and Cl2. That is a single displacement. And it's also a redox reaction, as is number 2. And finally, iron chloride and sodium hydroxide comes sodium chloride and iron hydroxide. That would be another double displacement. That's also a precipitation reaction, but that was not the question. So draw the dipole, appropriate dipoles on the following structures. Mark node by dipole if none is present. 2.1, 2.5, 3.5. It's trigonal planar, but there is a lack of symmetry on this molecule. So plus on the lower, arrow going up. Dipole. Now this is 4.0, 2.5. Very polar bond. However, it's tetrahedral. So all the outer atoms are the same. So it's a very symmetrical shape, means no dipole. That's 3.0. That's 4.0. Now this is trigonal pyramidal. While this is very polar, and this lone pair is not opposing, so we draw the dipole up here on the lone pair, plus on the lone pair, and the arrow going straight down. We have bromine. What's bromine from the chart? Bromine is, on the chart, bromine is 2.8. Chlorine is 3.0. Well, I was going for one thing. This should be polar if this was a polar bond. However, not really polar bond. So I'm going to go with no dipole just because it is a non-polar bond. Though I will probably give partial credit for anyone who puts this having a dipole. In this one, we have 4.0, sorry, 3.5, 4.0, 2.5. We're going to have this clearly a dipole pulling towards the oxygen. I mean, technically, this would have a dipole pulling up, but it's more or less going that way. Convert the following equation into a net ionic. Iron nitrate, silver perchlorate goes to iron perchlorate and chlorate and silver nitrate. So here's iron and silver. There's nitrate and chlorate. Iron, nitrate. So notice all these are aqueous. AQ, 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 AQ. Breaking this apart, you'd have Fe2 plus and 2 NO3 minus and 2 Ag plus and 2 ClO3 minus goes to Fe2 plus and 2 ClO3 minus and 2 Ag plus and 2 NO3 minus. Cross, 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 cross. Would have a net effect of no reaction because there's no driving force, nothing that forces them to swap. Okay, last question. Last question asks us to look at the following structure. Determine the geometries of this. The geometry of N1, which is right here, C4, which is right here, C9, which is right here, and O10, which is right here. So remember the lone pair, and this is a H bond. So we have a lone pair and H bond. It's an H bond, two lone pairs. Starting with this guy, there's 1, 2, 3 bonds, one lone pair. 3 bonds, one lone pair, that's 4 electron domains, one lone pair, that's trigonal pyramidal. So that means A, B, and D are out. C4, 1, 2, 3 bonds, no lone pairs. It's trigonal planar. So once again, that just knocks out D again. Okay, number C9, 1, 1, that's linear, knocks out none of them. And this guy, 1, 2, 3, 4. 4 electron domains, 2 lone pairs, means this guy is bent. So knocks out A and D again. So the correct answer is C. Finally, what holiday did we just celebrate last weekend? I should tell you the time. It was Mole Day, which is 10/23. This is Andrew signing off. Good luck.